We're going to start with carboxylic acids, which is basically a fancy way of saying these are the organic acids. So we call them, pen on, carboxylic acids. A carboxylic acid, which is a fancy word to say carbon and oxygen acid. It's a fancy phrase of just carbon oxygen acid, which contains the structural form COOH as a functional part of the group. So we get this double O in this particular form. So when we write it in condensed form, like if I write condensed here, it looks like this, RCOOH. No, it is not carbon dioxide without the H. I'll show the structure of it. So before I get past this, I want to point out what R is. Does anyone know what R might be? It's not an element. If you notice, look over there, there's no R's. So there's no R's on the periodic table. R is our standalone, that's terrible. Let's not do that. That's ugly. Let's do a quick, that's better. Draw, color, looks nice now. Okay, R is like your standard hydrocarbon. So it's like a generic chain. So any of our compounds that we've done so far can be like short-handed with R. And if we put this thing on the end of any R chain, so if it's a heptane or a butane or a cyclohexane or something like that, if we stick this on top of any of the just carbon-hydrogen mixes, we get this carboxylic acid. So when I draw the shape of it, it looks like this. R connected to a C, connected to an O, and an H, and this side is also connected to an O. So this is the shape of this particular object. It's a carbon double bonded to an O and single bonded to an O and an H. So remember, this is our alkyl group. Basically, any number of a chain on that side. So it doesn't matter how many are on that side. That'll change the name of it, but it'll be this carboxylic acid. So I should write that it's structural. In other words, it's showing the shape. That's the way it's shaped. So R can be anything it wants. It can be any of the alkane-alkene mess. It can't also be an alcohol. It can't also be one of the other ones. But yeah, basically not that. So the methanoic acid, how many carbons do you think it might have? 1 carbon for methanoic acid. So I'm going to draw it like this. HCOH, double bonded to O. That's methanoic acid. Let me slide it up so everyone can see. So that's methanoic acid there. It has a common name, often called formic acid. Don't worry, we don't need to actually remember that name. That's just for informational purposes name. You will call it methanoic acid because it has 1 carbon in it. Any guesses for ethanoic acid? 2 carbons. So we're going to do a H3C, double bonded to a C, singles, OH, O, like that. Ethanoic acid will be this particular thing. With a condensed form, which I'm going to show and see if anyone notices, if I write CH3COOH, that's also ethanoic acid. Does that look familiar to anyone? Yeah, what does it look like? It has a common name. Nobody? Okay. That's acetic acid. It also has an even more common name that you may have heard of. Anyone know a better name for acetic acid? No. We'll get to that. Yeah. That's vinegar. Yes, that is vinegar. Vinegar is acetic acid, and this is ethanoic acid. So ethanoic acid is acetic acid, is vinegar. They're just all different names of different things. The more common something is, the more likely it has like 4 names. If it's something super rare and doesn't get made very much, it'll have just the one proper name that's cumbersome. Yeah. A boring version of the butanoic acid, CH3CH2CH3COOH, is butanoic acid. I don't really have room to draw a full structural diagram of this, but I may do a line diagram of it. So I would do the line diagram would be like this, and then I would go 1, 2, 3, 4. I got 4 carbons there. So that would be the line diagram of it. If I'm counting, that's 1, 2, 3, 4 carbons, and then the other stuff. Okay, good.
Can you use an R for that?
No, because R tells me any number. It's just like a placeholder to show the shape of the fancy group. And so R is just like any. It's like a what's the word? Like a polynomial. It's like, well, isn't that just any? It's anything. It's an umbrella term. So it covers all the different chains, including the cyclos, including double bonds, including any other thing that might be stuck there. Good. So that's basically what carboxylic acids are. The next thing is called an ester. These are the things we're going to work with next week. They have a COO group in them. These are examples of something called an organic salt, which is fancy. It's basically the salt version of a carboxylic acid. So what we do is we have 2 different R groups on here. Is this all the end of this page? Okay. We can do R1COO, then R2. And R1 and R2 are just means one group of chain and another group of chain. They could be the same, they could be different. Yes?
Could you just write CO2 instead of having to pick both of them?
No. It's telling you. So it's kind of like phrasing. We write COOH in a condensed form to mean this like double bonded structure here. So that's what it means. Like when I write this thing, I mean this shape. So it's just like the reference. And so this is the shape of this thing. So this is going to be R-C double bonded to O, O, and then that's my R2 group there. So this is the other half of the esters group. So when we're naming these lovely things, this is the parent chain, and this would be a added group. Yeah.
Why is there a comma right in front of the R?
Where?
That's a 1.
It's 1. Yeah, 1 and 2. Fair enough. Good questions. Always ask if you don't know what I wrote down. It's a good practice. So it's like, why is there a comma? It's a number 1. Good. It's like sometimes it's like, why is there a 0? It's an O. Those are perfectly good questions. It's better to ask than not know. Okay, so for naming these, the hydrocarbon attached to the carbon side of the COO group, in this case, according to the way I drew it on the previous page, that's R1, the parent chain, has the E ending change, right? The E of the very ending of the word change, and it changes to O8. So not oat, this is O8. We like to say all of the vowels in chemistry class. So we like to put all the vowels in, we don't put them together. So it changes to O8. And this C is the parent chain. I said that here. I wrote it earlier, but it's now on this page when I say parent chain. And attached to the oxygen side is the alkyl group. Or like the functional group, a methyl group, ethyl group, etc. Okay, so we're going to name these 2 lovely things. What do they have in common? Well, they both have 2 O's because they're both esters, right? This piece here This little piece here is an ester. They're neither trans nor cis because that only works with double bonded carbons. These are carbons double bonded to an oxygen. So that naming convention doesn't apply here. So these are both esters because they have this particular piece in here. That's an ester. What do they? Well, they all have the double bond in here, but these both have, if I point out, 1, 2, 3, 4, 5 carbons. 1, 2, 3, 4, 5 carbons. They both have 5 carbons, but they're going to have 2 different names based on which part is going to be the parent. So for us, in the very first one here, we're looking, the parent chain is this one. This part is the parent. And this is the added group. So in this next one, I'll do it the same way before I write the names in. This is my parent chain. And then this is the extra group. I kind of missed that part there, but that's the idea there. So this is the group. And this is the group. So this is the differences. They're very similar, but they are going to be different because they're attached on different sides of the oxygen kind of pairing. So how do I name these ones? How many carbons are in my group? In the first one, the one on the left here. 1. 1 carbon is in my group. So my group name is methyl, right? How many are in my right one group? How many are in this group? That's 4 carbons over here. So this is a 4 carbon group. Yeah. 4 carbons in that group. So with 1 carbon in the group, we have the prefix methyl. So this is a methyl kind of compound. So I will write methyl. How many carbons are in my parent chain? 4. So this is going to be a bute something. So the naming is O8. So this is butanoate. Butanoate. Right, so this is methyl butanoate. It's a great phrasing here. Okay, given this particular phrasing, what do you think the other one might be? Good choice, Francois. I heard that. What did you say the first word was? Butyl is right. So we're going to start with the butyl group. And then what kind of O8 is it? Methanoate. Methanoate. So this is butyl methanoate and methyl butanoate. Similar, but not the same. So they have similarities, but which one is the parent is on one side of the carbon-oxygen nonsense, and the one is on the other side. So the one on the first side is the parent. So we have to try to draw these lovely things. How are we going to draw ethyl propanoate? So we're going to just do a little summary here. My summary will be 2 carbons in my group and 3 in the parent. So 3 in the parent chain because propane is 3. So it's propanoate is in the parent. Yes?
Does it matter which way you
Which way I draw it? No, it's which side is it attached to. The group is attached to the O side on this side, the way it drew it here. It's attached to the O, and the parent is attached to the double bond. So the parent is attached to the double bond, the group is attached to the single O.
Is that how you tell, like, where?
Yeah, that's how you tell which one's parent and which one's group.
Like, how do you tell where the double bond?
You can put it wherever you want. So the best place to draw it is just draw your base and then add on each side. So I can draw it this way. I'm going to write O double bonded to C over to O and start here. This is my ester. It has to start somewhere here. And then I'm going to have to put something over here. That's my group. And then something over on the other side. That's the parent. So how many carbons need to be a part of the parent chain? 3 for the parent chain. So carbon, carbon, carbon. So now my parent has 3, and my group needs 2. So I've got 1 and 2. Doop, 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 doop. Now I finished it. Yes, the 1 stuck to the double bond is included in the chain. So this is how the it's going to work. So ethanoic acid, let's draw a quick line diagram of it because I don't have a ton of space, so I'm going to draw a line diagram of it. Ethanoic acid looks like this. That's ethanoic acid. I'm going to draw methanol. What is fancy about methanol? That's an alcohol, right? Now I'm going to be a little clever with my ethanol. I'm going to be sneaky and say this is HOCH3. Yes, I drew it on the left. That was for later, but I'll show you in a second why I did that. It doesn't technically matter, but it'll work in my diagram. And then we're going to make methyl ethanoate. Which one is the parent? That's the ethan is the parent, so it's going to get 2 there. And a 1 over here. Just going to put that there. And we're going to get water. I knew that one. All right, so this is how it goes. So we can see where it's coming from. One of the things we're noticing is the methyl comes from the alcohol, and the ethanoate comes from the acid, right? So the alcohol will add to the group. So whatever I put on my alcohol will go to the group of the ester, and whatever I put in the acid will go here into the ester. So it'll go into the parent of the ester. Sorry, the parent. So the reason I drew this particular reaction in this way is you can see here how they went together. What have I circled here? Water, right? So that's where it goes together. That's how they meet together. The H and the OH come together. They make water. And so then this methyl group, you can kind of see here, this methyl group from here is going to go over and stick to that side here. This H comes off, this methyl group will come put on it. So that's where that goes. That's the kind of reaction here. So we know the first thing, ethanoic acid is quite literally an acid, right? What would methanol be as a kind of chemical? What kind of chemicals do you know that end in OH? What kind of chemicals end in OH when we're doing it, Piper? Bases. So what kind of reaction is this? When I put acid plus base? Neutralization reaction. So what did I call a ester in its initial description? Well, what do neutralization reactions make? Acid plus base equals? Water is one of them. That one was easy. I got water over here. What else does it make? No.
Oxygen.
Salt. And remember, we called esters organic salts because they're made through a neutralization reaction. So the ester is taking place of the inorganic salt, like a sodium iodide or something like that. One of the salts that you can make with organic compounds. This is an organic salt, an ester. So that's why I put it here. Technically, we have to add this lovely thing in the middle, H plus in the middle, because it's a catalyst for this reaction. Do you guys know what catalysts are? You guys remember that word? What? Science 10 should have taught you the word catalyst. Anyways, a catalyst is a compound that makes the reaction faster without doing anything in the reaction. It's not a part of the balanced reaction. It just makes it go faster. It won't work without it. It will just be too slow for anything to happen. kind of like if you just like put salt on top of, or whatever. No, I'm going to go into that.